Thank you. My talk today will be in two different parts. In the first part, we will focus on what changed in Dask DataFrame land, how we made it faster by a lot. And then the second part is mostly focused on benchmarking, where we look at Spark, DuckDB, and Polars, and how all four frameworks perform on a database-like benchmark set. We can keep this short. Thanks for the introduction. I currently work at Coiled. At Coiled, we do managed Dask clusters for our customers. So deploying Dask is basically what we do. My job, though, is developing Dask, the open source library. So everything that I do development-wise goes back to the community. Dask, at its core, is a framework that can be used for distributed and parallel computing. It grew popular because it integrates with the PyData ecosystem, with pandas, NumPy, scikit-learn, most of the tools in the PyData ecosystem that you can use have some kind of Dask integration available. Today, we will focus on data frames like tabular data. We won't look into arrays or any other weird shapes at all at the moment. It's mostly about how you can run MapReduce style queries. We will start with a quick demo, how Dask looked like 18 months ago. I disabled a couple of configurations that we've all added since March last year, so over the last 15 months or so. And we will now run a query. The details aren't important. We do a couple of filters and then a couple of merges before we do an aggregation in the end. I'll just kick this off. This is from the benchmark set that we will talk about later. Historically, Dask used to be pretty bad at these benchmarks. It always came in. Oh, this isn't. Oh, it's working. It always came in last on these benchmarks because we weren't doing much that was really tailored on performance. A thing you can see is I already triggered the computation, but there's nothing showing up down here. It just takes a little while until it took a little while until stuff actually got running. Also, the conference Wi-Fi isn't great, so that's not helping. Should get going in a little bit. And then we will see, I explain a couple of patterns on these graphs, and I point some things out that if you're an advanced Dask user, you're already familiar with that this is a pattern that you don't want to see on your clusters, but this will show up a lot here. Still waiting.
Could you please zoom in a bit?
Oh, yeah, sure. I don't know. It's not really doing what I wanted to do. I go back to the slides and we come back here in a little bit when this hopefully starts. Wi-Fi isn't great. The things that I disabled are 3 different things. We added a bunch of different improvements over the last year, but these are the 3 main ones that we want to focus on. It's one, we made joins a lot faster. If you're familiar with pandas or Dask DataFrame itself, pandas uses NumPy object to represent string data, which is bad for a number of reasons, memory usage, performance are 2 of those. Dask even has a third factor. It's NumPy object is Python, so it blocks the GIL a lot, which is terrible for a distributed framework. And then we look into the benchmarks a little bit, how Dask now compares to Spark, DuckDB, and Polars these days. As I said, previously it used to suck and come in last. This changed, but that's enough of a teaser. And then we look, we spend a minute on talking about what we intend to do in the future with Dask, performance-wise. Perfect, now it got going. What you can see here is this is the Dask dashboard. It shows you what's going on at any given point in time on your cluster. We have a cluster with 40 machines here that run in AWS. And what you don't want to see is you don't want to see a lot of white, which almost everything is white here. And you don't want to see a lot of red. And we have all these red bars. Both of these things are signs that your computation isn't as efficient as possible. We are processing 1 terabyte of data here, which normally doesn't take long, but with the old version will take quite some time. We won't wait until this is finished, because otherwise you'll have to give away like 30 minutes of your lunch break. We will now talk about the improvements, which will take us about 15 minutes. And if you're lucky and I don't get stuck somewhere, then this will still be processing when we come back. We start with arrow-backed strings. Apache Arrow is a library that like initially promised like efficient string manipulation operations in memory. It was integrated into pandas like a couple of years ago, I think, like in 2020 actually. And like in Dask, it's used by default. So every string column that you have in a Dask data frame will just be PyArrow-backed. This is nice performance-wise. It just like cuts your runtime in half if you do any string operations. You can also get a 10x improvement. It really depends on what you're doing. But in my experience, like Dask users don't care as much about performance. They care more about reliability. If you trigger a job on like 50 terabytes, you want it to finish and not like break down somewhere in the middle. And what helps a lot is that arrow strings use a lot less memory. They have just a more efficient in-memory storage model. This means that like memory is roughly cut in half to like maybe even to 30% of previous usage. And this is like with a couple of string columns. The data set we used here had like 4 string columns out of 20. And we still cut memory from like 220 gigs to below 100, which this is the actual like game changer for Dask developers. You just can get away with way smaller clusters, and even if you have a bigger cluster, it's way less likely to run out of memory. Out of memory errors are a pain to debug, to be honest. This was relatively easy. Like everything was already there. In pandas, we just had to like turn a couple of toggles to get these strings by default and not like end up with NumPy object and then have to convert back. The second bigger improvement that we did is a more efficient like join algorithm. Like a lot of the red that you saw initially on the Dask dashboard went back to like having inefficient joins, where a lot of like transfer was happening that wasn't really necessary. And so this was actually the first improvement we took live. It made everything that's related to like communicating between different machines on your cluster. Like if you do a merge or a join, you have to move all the data around over your whole cluster. It's a lot of network transfer, and that's inherently slow. Like network transfer in the cloud is maybe 200 megabytes per second. In-memory transformations are like 10 gigs per second. So you are naturally just a lot slower with network transfer, but Dask was even less efficient on network transfer. So we cut these like 200 megabytes probably to like 50 or so. One big problem was that we just overloaded the whole system. If you had a big shuffle, like shuffling is what happens before you can perform a join. And the number of like tasks that the system had to handle grew with log n times n complexity, which like obviously is bad. N is the number of chunks that you have in your data frame. So if you increase your data set size by 10, then it will increase by times 10 times log 10. And especially if you scale it to the terabyte scale, this is just bad. The new shuffle algorithm like hides a lot of this complexity away from the system and just grows linearly with growing data set size, which is something that Dask can easily handle. That's not a problem at all. This illustrates a little bit. We won't go into this in detail. Like you could probably talk for 2 hours about how we improved the shuffle algorithm and wouldn't cover all the details. The main gist is that we had an intermediate layer previously that was like this growing like task size, just log n times n, because everyone had to communicate with everything, and this was illustrated through a task that the system had to handle previously. Now we hide this away from the whole computation, and we just have one single task. So the number of tasks is actually determined by the in and output partitions. Depending on what is larger, this will be the complexity that the system has to handle. We will see later how this like reflects onto the computation, but it makes everything a lot more stable. The old algorithm, independently of the like complexity, a disadvantage was also that it had to keep everything in memory at some point. So your whole data set had to fit into memory. This is a little bit like the problem that Spark has. Your cluster has to be bigger than the data set you want to process. Now we use the disk in the backend, so we write stuff to disk while shuffling. So you can process like 10 terabytes with a cluster that has 500 gigabytes of RAM. So you can do heavily out-of-core processing, which is helpful if you're in constrained environments or just don't want to like spin up huge clusters all the time. The third thing that had the biggest advantage was historically Dask you gave Dask a query and it ran this on the system. Like it sometimes would fall over, would complete, didn't really matter, but it didn't touch the query at all. So whatever you wrote up was executed. Now we added a query planning layer that reorders whatever you provide to make it like more efficient. We'll see later how like big the factor of less data processed actually is. 3 steps are the main things that bring at least the biggest advantage that we've seen in our benchmarks. The first one is like a general optimization that every like SQL-like framework does. Polars as well, for example. Column projection and predicate pushdown. This means that we drop columns as soon as we don't need them anymore. Like ideally, if you have a data set with 50 columns, and you only need 2, you would only read those 2 from S3, Google Cloud Storage, your local disk, whatever, and would never load everything into memory. And filters just mean that you execute filters as soon as possible. So you push them all the way up to where you're reading the data, hopefully. What we see here is like we read from Parquet, like 2 potentially huge tables. And then we do a filter that is like restrictive, not restrictive, that's something we don't know. And then in the end, we just care about 2 columns, customer key and order total. So we want to calculate the order total per customer over like since 1995. Historically, Dask would like just read everything, like being pretty dumb, to push everything through the join. As I said, if you have a network transfer, this is pretty slow. So if you have a lot of data to transfer through the network, this will be even slower. Then it will run the filter and do the group by aggregation in the end that restricts us to 2 columns. This is where a query optimizer is very helpful. Like you could do this by hand. It's a pretty toy example, so it's very easy to see where each column belongs. But if you have a query that's like 100 lines long, or if you have a data set that has like 500 columns and you need 126 from them, then you don't want to write this down constantly at hand. And this is where the optimizer comes in helpful. Like it looks at the query and figures out which columns you need, and then it restricts like this immediately in the Parquet call. So we only read the columns that are absolutely necessary, nothing else. The same thing happens with the filter. There's really no reason that the filter happens after the join, so we can swap both operations, and in practice, Dask will actually move this also into the read Parquet call, but illustrating was hard, so that's where we are. As I said, this is a general purpose technique. Like operating on less data is always helpful. Doesn't really matter if you work on a single node, multi-node, or whatever. Even if you run on GPUs, just having less data is very helpful. The other 2 steps that I want to talk about are things that are more Dask specific or distributed computing specific. We as Dask developers, we know a lot about where Dask is good at and where it's bad at. And normally users shouldn't be aware of that. So we can like let a lot of our knowledge flow into the optimizer, which in turn makes user queries more efficient. Auto repartitioning is one of the steps that we added. Dask is a chunked pandas data frame. Like Dask data frame with 1,000 partitions just has 1,000 tiny pandas data frames. What Dask can't deal very well with is if these data frames are very small, because then there's a lot of overhead involved in processing. If each and every one of your data frame has like 2 rows, then computing anything on it will be really, really quick. And like Dask as a distributed system has some overhead. So if you have too many of those, then the overhead will dominate your computation. And even if you would like use 10 times the number of workers, like 10 times the amount of compute, you wouldn't get any speed up because the like scheduler, which is the master node, actually restricts like what you can do. And so what the optimizer does is it looks at like your input data source and checks out how much columns you want to select from those. And then it will squash many of them together if possible, so that we just reduce the number of partition count and keep a consistent size of each partition that we know that works very well with Dask itself and not like strains the system and whatever. This is also like a problem that we had previously with the old with the old system, it was just like overloading the scheduler constantly, and so like more compute didn't actually help in any way. This is what the lot of white that we saw initially. Like if there's a lot of white, then the scheduler is the bottleneck of your computation. So if we select half of the columns, then we will just like reduce the number of files 10. We will translate this into 5 partitions and instead of just keeping every file into a partition. There's also like a minimum threshold of size. If you have tiny Parquet files with each and every one is like 1 megabyte, then we will squash them together automatically to create at least, I think, 100 megabyte partitions instead of like 1 megabyte partitions. And this was a like 3-line code change and gave us like, I think, 2x improvement on every query on average, which I wish there were a couple more of them, but that's what it is. The third thing is, again, specific to distributed systems. Merges and joins are very, very expensive. It's the same with sorting in a distributed setting, because at some point you have to look into every partition to like place them in the appropriate place so that the merges actually work. You can't have like a 1 in the first and the last partition, because then Dask really, some of the merges will run into empty space. And if you do 2 merges after another onto the same column, historically Dask was just like, it shuffled for the first one, which is an all-to-all network communication. That's very expensive. And then it did the same for the second one. Even though like we already know that we already like put everything into the appropriate place after the first result, so that this isn't really necessary. So this is like what the query would look like. You had a shuffle initially, and then you had another shuffle join in the second step. Like each shuffle join is like 2 shuffles, so we got 4 in total. Dask now looks at this and figures out that the like second one was already shuffled before, so we don't actually need this anymore. So we just inject another shuffle specific node over here and do a trivial join, which is basically a pandas join, but on every partition. Like this is a toy example, obviously, but if you have 5 or 10 merges after another, which is quite common, and you don't have to like, you can reduce the number of shuffles from like 20 to 5. This is like a big win performance-wise. And also stability-wise. Like if you send a lot of data over the network at some point, if a worker dies, something might go terribly wrong. Summarizing, like you could do all of those things that I showed if you like really invested a lot of time into learning how Dask works internally, and then you had to write very ugly queries to get the same result. Now this is just stuff that the optimizer does automatically for you. It also like memory is lower, like the system is more stable, so it just scales a lot better to like 10 terabytes. We started running benchmarks on 100 gigabytes, and the old system worked like fine. And then we scaled out to 1 terabyte, and the old system just didn't get any of those queries done. And now like the new system is just churning through like 10 terabytes on the same cluster size, and it really doesn't matter. We can basically scale out a lot further without ever worrying about size of cluster and whatever. This is like a chart that illustrates the journey, and we will go right back to the cluster to see what this actually means. A little bit over a year ago, Dask was up here, and now we are like 19 times faster, basically. This is a representative query from the TPCH set. There are queries where the improvement is bigger, and there are queries where the improvement is a little bit slower. This is a good average over all of them. And you can see that all 3 sections like contributed at least significantly, but the biggest factor by far was the optimizer in the end. Just operating on less data and making everything more efficient is like a big win. And now we go back to our cluster. As we can see, this one is still running. Still churning along happily, but yeah. I think I'm talking for like 16, 17 minutes now, so this isn't very good. And this over here, it just doesn't set any of these configurations to the old values. This is like the latest release of Dask, and it's just like a default query, no specific configurations. The first thing we can see is a lot faster. Like it's already started while before I had to wait a long time. And we can also see there's a lot less white involved. There's no red at all. So this system is just used a lot more efficiently. We have to do a group by in between, so a little bit of red is expected just to do, I think it's a sum. But it's not really much. Everything else is utilized very, very well, I would say. And there's not much time where the system is just idling around. I mean, if you spin up a cluster with 1,000 workers, this gets expensive really quick. And if like 900 of your workers don't do anything, that's very annoying as a user, and especially as someone who has to pay the bill at some point. By the way, I'm not cheating. The clusters have equal size. Both of them have 40 workers. There's no difference in hardware or anything. And as we can see, like, we are finished now in a little bit. This is basically the 19x speedup that I talked about earlier. Like, you can just fire up the query and then it's finished a couple seconds later. While previously, like, you could drink like 1, 2, 3, 4 coffees. I don't know. Depends a little bit how fast you drink. I launched those clusters with Coil because it's just like 2 lines of code. And another thing I want to show is if you refresh this here quickly, hopefully my Wi-Fi connection is stable enough. Like, this is our new computation. It had like a couple thousand of tasks and it processed 120 gigabytes. I want to focus on the 120 gigabytes. It's a 1 terabyte data set, but we didn't need all of that, so we could trim it down to like just run stuff on 120 gigabytes. This is the interesting part. It's not finished yet, but it's already processing for like 17 minutes. And it processed 6 terabytes of data. The data set was only 1 terabyte, so we are messing with the data around so that in the end, it will end up at like 8 terabytes. So we just like process like 40x data less, and that's where a lot of the speed up comes from. And like the optimizer, the shuffling, all of that like plays into this. We can also see, if you look at the worker distribution here, this is the CPU and the memory. Like, memory is pretty strained. And CPU is like not very well. If you only utilize like 25% of your CPU, that's like not great. You could theoretically do a lot faster. If you look at our new computation over here, then we see that CPU is okay, and like memory is barely noticeable. Reducing the amount of data by that much requires us to hold a lot less data in memory. And like, if you would like run the same hardware specification with like 10 terabytes, this would complete fine. It would just take a little bit longer. It's like now mostly about what you want wall time wise. Like, if you are fine waiting a little bit, you can process a lot of data with like not that much hardware. Now we go back to the like second part of the talk. Like, if you remember, like, it's a 19x improvement, let's call it 20x. And then we wanted to see how we stack up against Spark, DuckDB, and Polars, a little bit more limited. All 3 tools have Python APIs. Spark and DuckDB have a SQL interface. Spark has been around the longest, like for 15 years now. And we use this PySpark, the SQL interface. And DuckDB is one of the newer tools. And then we compared, like, we had Dask with our DataFrame API, which is basically pandas, but in bigger. And Polars, which has its own API and runs in Rust. And it's pretty fast on like smaller amounts of data. TPCH style is like a lot of like joining and grouping. It's like a little bit, it's closely related to databases, how databases benchmark their stuff. We ran them on a variety of scales. Like, we don't really care about 1 or 10 gigabytes. That's something where you can use another tool, and Dask is really like, the hammer of Dask is too big for that. So we focused on 100 gigabytes, 1 terabyte, and 10 terabytes. All tools got exactly the same amount of compute available, but like, since DuckDB and Polars are both single node engines, they just got a huge VM, and Dask and Spark perform better on many but smaller VMs. So we gave them like a cluster of different machines. But the amount of CPUs and the amount of memory was exactly the same. The 100 gigabyte scale, this will get a little bit crowded. I'm sorry for that. And we put all 4 engines into the same chart. This is not super important to us, but the thing we came away with is that Dask is now actually okay. Like, we are on par and a little slower than the single node engines on most queries, but we are actually competitive now instead of like timing out for every query. DuckDB is very, very fast. DuckDB on this scale is probably the fastest tool you can use. So if you have 100 gigs of data, then DuckDB is probably the tool you should use if you're fine with a SQL interface. Like there are people that don't like SQL, and then like it's a little bit harder. Polars performs well on the more simple queries, but they tend to fall over that scale for the bigger ones. Like if you have a lot of joins or complicated like query structures involved, then they can't complete them yet. They ran into like our timeout was I think like 500 seconds or so, and they didn't complete them during that time, even though they were still like doing stuff. They weren't hanging or deadlocking or whatever. I suspect that they get there in a couple of years. They are moving pretty fast, but the engine is just like the newest of all of that. And PySpark, like this is clearly not yet big enough so that PySpark can actually be fast. Like it's the blue bar, and it's like the slowest on most queries, except the ones that Polars timed out. So yeah, for 100 gigs, the takeaway is probably stay with DuckDB or go to DuckDB if you need to. For 1 and 10 terabytes, we skip Polars because like that just ran forever and it's actually expensive. So we will now look at Dask and DuckDB, and then we look at Dask and Spark. Like it will become obvious in a little bit why we can't compare all three of them at once. Sorry. The main takeaway here is like it's actually pretty competitive. Like Dask is faster on a couple of queries, DuckDB is faster on a couple of queries. It depends a little bit on what you're doing. The queries that Dask tends to outperform DuckDB are the queries where you have to process a lot of data. Like some of those queries, as we've seen earlier, like 1 terabyte, and we processed like 100 gigs, so it's like roughly 10%. The queries that reduce very much is where DuckDB is pretty good. But they tend to struggle a little bit with out of core if you just have to hold a lot of data in memory at once. But it's a pretty even picture. Like it depends on what you're doing. Like both tools are valid choices. It was also not very much out of core. We had like 50% of the memory available of the size of our data set. So DuckDB can definitely handle out of core. They're just not that efficient on that. And then we run 10 terabytes with like 500 gigabytes is the biggest like reasonably priced instance you can get at AWS. And we noticed that DuckDB, like if it completes queries, it's actually pretty fast. But the queries that it struggled with before are queries now where it runs out of memory and fails to allocate memory at some point. But it's not built for 10 terabytes. So this is not super surprising. But we were actually quite surprised that it was performing that well on that scale, even though it's like a single node engine with like 500 gigs of RAM. The thing that we liked about Dask is that we can like process basically everything except query 5. With a factor of 20x out of core processing, like 10 terabytes, and we can do everything with 500 gigs in RAM, was a result that we were happy with. Again, Dask is a distributed computing framework, so we care a little bit more about the comparison against Spark than DuckDB. The first thing we see is that Dask actually outperforms Spark on 1 terabyte on most queries. Like, again, if you remember, Dask got 20x faster. For example, the 20x improvement is on query 3. So if you multiply our runtime by 20, then like Spark really kicks our ass. So now we are competitive, which is like what we were aiming for. So at 1 terabyte, it mostly comes down to usability, UX, ecosystem, whatever. Like performance is not really a huge consideration anymore. Like previously, you really had to spend a lot of time investing into optimizing Dask workflows to actually get good performance out of it. This is not a concern anymore. Interesting is the comparison on 10 terabytes. Like we tried running Spark on 500 gigs of RAM, and that did not work at all. It was like processing on the first query, which takes like, I don't know, 30 seconds or 40 maybe on 10 terabytes. It was like processing for 2 hours. And like CPU utilization was still at like 100%, but nothing was happening. This is why we can't like put them into the same chart with DuckDB. It's just like it doesn't work on 500 gigabyte of memory. So we tried on 5 terabytes. And surprisingly enough, it worked now. So we actually got results for some queries, but it's like still failing with timeouts for the queries that are more involved and require calculating on a lot of data. So our takeaway here is like Dask is now actually competitive performance-wise, and it is a lot better on out-of-core processing. It's a little bit like stupid to run 10 terabyte queries on like 15 terabytes of RAM. That's why that's not included here. So the main takeaway is like DuckDB actually is like performs pretty well. If you have a scale where DuckDB is a good fit, then it will probably be the fastest tool, simply because DuckDB doesn't have to worry about network communication. They are all on a single, everything's on a single machine, so you don't have this like very expensive shuffling transfer that Dask and Spark have to deal with. Spark is reasonably fast, but on larger scale, on smaller scale, it's like very slow. So if you run it locally, then DuckDB, Dask, and Polars will all kick Spark's ass. But it needs a lot of resources to actually get anything done. So processing stuff heavily out of core is not really an option. The thing that we're happy about is like Dask got 20x faster, and we are now actually on the same scale as Spark and DuckDB. Previously, this was like not good for us. But there's still a bunch of like improvements that we can make to especially improve on a couple of those queries. They are not very expensive computation-wise. For Dask, like 50% of the total runtime was just overhead that we had while submitting the computation to the cluster. And like if you just compare runtime, like it's not how it works, I know that, then Spark and Dask are actually equally fast. Like we identified like 50% of overhead for some computations when the scheduler gets ready to actually submit stuff. This is something we'll hopefully be able to optimize relatively easily. Like there are 2 or 3 areas, if we get rid of them, then we should be good. Shuffle is also like currently, it's a lot faster, like 3x faster than before, but it's still slow. Like faster just means that it's not as bad as before. There's still like a bunch of constant overhead that's especially relevant if you have a huge data sets that we can hopefully get rid of. And like our query reordering is still like pretty dumb. We only do the things where we are like perfectly certain that they will improve your performance. This is something we found with Spark while benchmarking. There are a bunch of things that you can turn on in Spark, but they might actually make your performance worse. So that's why our query optimizer only changes the order of your execution order if it's very certain that the performance will actually get better. We don't do much join reordering at all at the moment, simply because like this is a little bit of a fuzzy area where sometimes like executing them in one way is faster and sometimes in the other. It really depends on how the join works. If it blows up your memory, then it might need a completely different ordering than if it doesn't. But this is on our roadmap, and we'll hopefully be able to get this in at some point over the next couple of weeks or months. And like we messed around a little bit with the join ordering manually, and there's like probably an order of magnitude for some queries, and it won't matter for other queries. So it's like maybe 2 or 3 queries get an order of magnitude faster, and the others like just won't care at all about it. Yeah, that's it. Now we have some 5 minutes for questions. I think he will bring the mic.
I can be loud if I need to. Maybe I'll just be loud. Very nice talk. Very impressed with what you've done. Genuinely, really impressed. I might even go and try Dask, which I haven't used very much. But as much as I love what you've done, I really hate your graphs. What I hate about your graphs is that you've drawn graphs that when you're twice as fast as something else, the bar's twice as long as when you're half as fast.
That's true.
That is snake oil. That is. I mean, I could talk about all this yesterday, but that is like. Darrell Huff has this book, How to Lie with Statistics. You're lying with statistics, even though you've got fantastic statistics. You don't need to lie about.
That's true. We tried scaling this, but it was tricky.
You should show the time difference. You shouldn't do multiplicative stuff if you're going to have one going down and one going up.
That really didn't tell anything. Like the problem with those queries is that some take 20 seconds, and the other take like 500. And so even if you're like the same performance on the 500-second query, then everything else won't matter anymore.
Okay, then you should draw the graphs both ways up so that Dask is sometimes on the bottom, not the top, and you can see it really looks wrong.
Okay.
But I love the tool.
Yeah.
What versions of the different packages did you compare against? Because DuckDB recently had 1.0, and I don't know if you benchmarked.
We benchmarked on DuckDB, I think, .9 and .10. And the difference wasn't really that noticeable. We haven't rerun stuff since they released 1.0. So it's the latest release before 1.0 for DuckDB. It's the newest PySpark release, and like Dask is also like a couple weeks old. And Polars is not 1.0 yet, but the release before that, if I remember correctly. 1.0 is only alpha, I think so. Yes?
Have you thought about benchmarking against ClickHouse?
No. Like we mostly care about Spark, to be honest. This is like the direct competitor of Dask DataFrame. And like DuckDB is used a lot, so it's nice to include in the talk. If someone wants to, like our benchmark repository, that's something I didn't say, is public. So if someone wants to contribute ClickHouse, that would probably get accepted, but we are unlikely to invest effort in this ourselves.
I have two questions about Optimizer. The first one is it stateful, or does it use information from previous round about the same workload?
No.
And the second one is, do you provide, in the Optimizer, because you make decisions, do you provide some diagnostic events so that a person could just change their queries and never try running them again, so that they have to be optimized? And because you're making those decisions, you can also expose them in the events, for example.
No, we don't do that. If you execute the same query like 5 times, the optimizer would run 5 times.
Do you have any output out of Optimizer?
You can write it away, but that's not what we do by default.
When using Spark, you can do like a broadcast join when you have a large data frame and a small one. Do you support that in Dask? And also in Spark, it's not
Yes.
hidden from the user. So do you shuffle, like, is it hidden from the user as well?
Yes, like what we do is like we look at the number of partitions, which is just the number of like pandas data frames you have, and then we make a decision based if we should use a shuffle broadcast or if we can use a trivial join. Like if one of your sites is only like 1 partition, then you can join trivially without having to shuffle at all. But it's like you can specify this manually, but the optimizer does this for you, so you don't have to worry about it normally. Except if you know more about the data than the optimizer does, then this might be a helpful configuration. Yes, and then.
Basic question about Dask. I don't know much about it. I was just curious, is it Python like all the way down, or you mentioned some of it's built on top of PyArrow now? Is it like on top of anything else?
Dask itself is a Python package only, but all the processing is done by pandas. And pandas like uses Arrow. We use like Siphon code and C code, so that's compiled. But Dask itself is like Python only, and like. It also runs only pandas, so the Dask DataFrame integration. So you get pandas, arrows, and whatever. Yeah.
Have you tried running some of the benchmarks with Dask and PDF? Like I saw that it's supported for a number of operations, but not everything. But I don't know if like.
We also have contributors from NVIDIA which have run stuff on Dask QDF, but I don't have any up-to-date numbers. Over there is like. Like, I'm a pandas and Dask maintainer, so this is kind of my task. Yes, we looked a little bit into this, but the 2 big advantages of the pandas free release will probably be that we turn on copy and write, which will mean a lot less copying, which is very helpful for Dask because you don't have memory spikes anymore, but it won't help much performance-wise because leg network dominates everything. And the second one is that arrow strings are enabled by default if you have PyArrow installed in pandas. And that's actually like what we do anyway, but like our API will become a lot simpler and a lot more efficient if pandas handles the transformation. On these benchmarks that I showed, like pandas really doesn't matter much, to be honest. Like total runtime of pandas is like 10% of the overall runtime. This is also like, I haven't gotten this question yet. I got this for every other talk I give. Why a Polars integration doesn't make much sense at the moment, simply because like even if you could get the 10% down to 1%, it wouldn't change the big picture. So pandas is actually like already reasonably fast for us.
I was going to ask also Polars.
Yes?
Is there like a way of getting a high-level overview of how Dask does the computations across multiple nodes? You know, how to allocate resources across various CPU?
The best thing is, like, maybe this is it's still running. The best thing is probably the Dask dashboard to figure out what's going on each individual node.
No, the question is, how did you design workflow optimize? Because you see, obviously, high-level diagnostics, but you have to refactor the code base, right?
What we use for benchmarking is, it's a benchmarking tool called PySpy, and there's a Dask integration, and then you can look where you actually spend compute time over your workflow. And this really shows bottlenecks quite efficiently.
So what's the name?
PySpy. Yes?
Do you think about some kind of partial recovery, because you have some tasks failing which you could try running on a different program to kind of go after this?
Dask does this by default. I think you can configure the retry. I think the default is 4, so it retries the same task 4 times on. Yes. Yes. Any other questions? Otherwise, we can all go to lunch.